last time we looked at merge sort, and we did an analysis of the running time by setting up a recurrence relation that mirrored the recursive structure of merge sort. So merge sort on a list of numbers of n numbers, we saw that running time was n log n. And the way we did that, again, was by setting up a recurrence relation which said that the primitive number of operations on a list of size n was 2 times t of n over 2 plus n. Well, actually, it was n minus 1. And then we said f of n, t of n less than or equal to f of n is 2t n over 2 plus n. And then we drew out a recurrence tree for this recurrence relation and saw that every level of that recurrence tree left behind an n. And the number of levels of that recurrence tree was log base 2 of n. And that's what ultimately gave us the total running time is bounded by n, the function n log n. And we didn't have to specify what the base of the log was because log n, no matter what its base is, differs from log n of a different base just by some constant number. And so whatever constant here and whatever constant here you have will just disappear when you're looking at big O notation. So that went away. Okay, so then I asked you to take a look at another recurrence that will just solve for the sake of getting more technique on solving recurrence relations. This doesn't necessarily mirror any algorithm that I know of, although it's not an implausible one. T of n is equal to 4 t n over 3 plus n over 2. Okay? So I think what I asked you last time to do is to start unwrapping this and see if you can see the pattern. So hopefully some of you have done that. So let me remind you again, what's the game plan? We're going to unwrap this recursion, which means we're going to pick a value of n that's convenient for doing this investigation or unwrapping. So you see that n is being divided by 3 each time. So it's a good choice is a value of n that's a power of 3, maybe 27. The 4 here just tells you how many ways you're going to branch. So that doesn't influence what n you should pick. It's what you're dividing by that has the influence on what's a good choice for n. So you unwrap that to see what's going on, and we'll do that in a minute. And then you, from that unwrapping, hopefully, you see a pattern, which means that you can express the sum in terms of n itself, of n. So you don't just do it for n equals 27, but after you play with a particular example like 27, then you see what the pattern is, and you can at least express a sum in terms of n. So you've generalized. And then you solve the sum as a function of n. And last time, the solving part was just noticing that every level in that tree had a sum that was being left behind, which was n, and therefore the sum was just the number of levels times n. So that summing was particularly simple. Solving for the sum was particularly simple. That isn't always the case. And in this example, we'll see we're going to have to bring in high school level mathematics to actually get the sum. Okay? So let's start this unwrapping. We want to know what t of, well, okay, I said 27. My little picture, I already had t of n. Let's see if I can be flexible enough, usually not, but let's see if I can be flexible enough to work on a specific example that I hadn't worked out ahead of time. So t of 27 is, according to this recurrence, okay, it's 4t of 27 divided by 3, right, which is 9. So we want to know what t of 9 is. Okay. Oh, I forgot the base case here. That's just t of 1 equals 450. Okay. So according to the recurrence relation over there, t of 27 is 4 times t of 9 plus what? Well, that's not so pretty, is it? 27 divided by 2. Well, all right. But anyway, it is what it is. And so this is the summation part. Okay? So t of 27 is 4 times t of 9 plus 27 over 2. So the 27 over 2, we know that's going to contribute to the sum that we're going to get for t of 27, but we need to know what these are. Okay? Well, I need to know what t of 9 is. Okay? Well, I don't know what t of 9 is, but I do know that t of 9 is 4 times t of 3. 9 divided by 3 is 3, plus 9 divided by 2. Okay? That's what each t of 9 is 4t of 3 okay? I'm not going to write out the other ones. So we have 4 of those, t of 3. Each t of 9 leaves behind 9 over 2, right? Okay? So what is in the sum at this level? Is what? Okay, you've given a specific number, but can you say it in a way that's that gets us a little closer to seeing the pattern? 4 times 9 over 2. Yeah. 4 times 9 over 2. Okay? The 9 over 2 comes from here. This is t of 9 is what we're looking at, 9 over 2, but there are actually 4 of them here. So from this level, what's being added to the sum is 4 times 9 over 2. And here, just for emphasis, I'm going to make that 1 times 27 over 2. So 1 times 27 over 2, this is 4 times 9 over 2. Okay? Now we need to know what t of 3 is. Okay? Well, I don't know what t of 3 is, but according to the recurrence, it's 4 times t of 1. Okay? Plus something. T of 3 is equal to 4 times t of 1 plus 3 over 2. Okay? So 3 over 2, but how many of them do we have? What? 16. Okay? So we have 16, but that's also known as 4 squared. Oops. 4 here is equal to 4 to the first. 1 is equal to 4 to the 0, right? Okay? So 4 to the 0, 4 to the first, 4 squared, that's 16. All right? Well, okay. The 16 is equal to 4 squared, not 4 squared equals the whole thing. Okay? And then what about the T1? Okay, each T1 is 450, and how many do we have of them? 64 of them. But to be more suggestive in terms of the overall pattern, 64 is what? 4 to the third. Times 450, which is the T1. Okay, and then we're done. All right, so now that we've done a particular example with n equals to 27, what you would like to do is go back, I'll do it on a different board, and try to map this out in terms of an abstract n. Not 27, but just n. So it looks sort of like T of n is equal to 4 times T of n over 3, T of n over 3, plus, here's the summation portion of it, n over 2. Okay, n over 2, but that's also equal to 4 to the 0 time. Well, let's go a few more steps before I put in the general form. Okay, then T of n over 3, what's the next one? Well, it's T over n over 3. We plug that n over 3 in here. That's n over 3, and so what will this be? N over what? N over 9, right. So this is now n over 9. And you can see how this is mirroring what we have over there when n was 27. But in general, this is T of n over 9. Okay, and of course, we have one of these for each one of those. Okay, so that is now yeah, this is n over 3. Okay, we're at n over 3, and this is supposed to be n over 2. Okay, so it's confusing because we're using n in the same sentence but in two different meanings. One n is on this side and one n is on that side. So n over 3, and this is n over 2, so what am I really thinking of? N over 6, right. Okay, and how many do we have of these? 4 of them. So that's 4 times n over 6. All right, let's just go one more level before we start to see the pattern. And then each n over 9, T of n over 9 becomes T of what? Well, we have n over 9, and here's n over 3, so that's n over 27. Okay, you're getting it. Okay, but how much is left behind here now? We have 16 of these guys, right? And this is n over 9. So when n over 9 was on the left side, this over here is n over 18. Okay, so what's the pattern? Let me call this level 0. Level 1, level 2, etc. And what is being added, what's being left behind at level I? At level I, what is being contributed to the sum? See the pattern? Okay, this is, let me just for emphasis, that's 1 times n over 2, 4 times n over 6, 16 times n over 18. So it's pretty clear that these guys are going up by a power of 4, by a multiple of 4 at each step. Okay? What's happening over here? You're dividing by, this is 2 initially, and then this is 2 times 3, and this is 2 times 3 times 3. Okay? So I'm sure everybody, if you went home and looked at this and played with this yourself, you would see the pattern and be able to describe it in terms of n. But let me just show you what that is. At each level, 4 to the I times n over 3 to the I times 2. Okay? And you can see this is level 0. So we have 4 to the 0, which is 1, times n over 3 to the 0, that's also 1, divided by 2. So that works there. Let's take let's take I equals 2. I equals 2, we have 4 to the I, 4 squared, 16, times n divided by 3 to the I, which is 3 squared, which is 9, times 2, which is 18. So this is the general, I'm claiming this is the general pattern. Okay? Now, if I wanted to prove that this is the general pattern, how do I do that? Induction, yeah. I mean, yes, absolutely formally by induction, you would say this is the pattern down to some level I, okay? And then you're interested in what's the sum that's left behind at level I plus 1. And how do you get that? You get it by, by applying the recurrence there. And now maybe you'd actually want to say, prove inductively, how many nodes you have at each level I, okay, and so on. Yeah? Why is level 0 not at the root? Well, I could say, okay, this is level 0, and this is level 1, and so on. And it's this piece came from T of n, and I see what you're saying. That would make more sense if I'd put this up there parallel with T of n. But this is, you want to think of it this way, this is the levels of the sum. And so this first portion, this one here, comes from here, if you want to call that the levels of the tree. So level 0 of the tree corresponds to level 0 of the sum, and it would have been better to write them at the same height. But anyway, those are the correspondences. Okay, so we've got this, we know what is being left behind at each level of the sum. So now T of n, abstractly, just in terms of n, is equal to the summation I equals 0, the number of levels, 4 to the I times, well, I'm going to take the n over 2 out. N over 2, so it's 4 to the I times 1 over 3 to the I. So 4/3 to the I. Okay? So there are two things that are left here in order to finally get a closed form solution in terms of n. We have to know how many levels there are. Okay? Now, when we were doing merge sort, we were doing the recurrence relation for merge sort, n was being divided by 2 each time, and the number of levels was log base 2 of n. So that was pretty simple. How many levels are there now? Yeah? How about what? Oh, yes, and T1. I'm sorry. Yes, definitely. Okay, so we want to know, so we should say how many T1s do we have? Okay, so we're going to have 450 times the number of T1s. So now there's really three things we have to figure out. How many levels, okay? How many T1s are there? Each one contributes 450. And so that's the first two things we have to know. And then, knowing the number of levels, we'll want to solve this. We don't want to leave it in a summation form. We want to get a nice closed form solution for it. Okay, well, how many levels are there? Log base 4 of n is, I heard that suggestion. Where does the 4 come from? You're talking about this 4. Okay. All right. Well, what we're seeing, though, is that the successive divisions are dividing by 3, though. We're starting out with n as our initial number, and then at the next level, it's n over 3, and the next level, it's n over 3 squared, and so on. So you go from n dividing by 3 successively until you get down to 1. So how many divisions of 3 are there? Log base 3 of n. Okay, so the number of levels is log base 3 of n. Now, everything is nice if you're talking about n being a power of 3, or previously n being a power of 2, and so on. If n was not an actual power of 3, then you'd want to, upper round it, or lower round it, and so on. And after a while, you get a sense of when those roundings matter and when they don't matter. Almost always they don't matter in this class, in this kind of analysis that we're doing. Ultimately, we're just going to get to a big O notation, something of that level of precision. And so if I do this summation thinking that n is a power of 3 and just leave this as log base 3 of n, we'll get an answer that's perfectly informative. Okay. So that's that. Now, how many T1s do we have? Okay, now we have the multiplicity of 4, because each level we're branching 4 ways, and we branch each one of those branches 4 ways, and each one branches those 4 ways. So your suggestion was 4 times log base 3 of n. Okay. 4 to the power. 4 to the power of log, because it's 4 times 4 times 4 times 4. We're branching 4 ways from each node that's in this tree. So it looks like it should be 450 times 4 to the log base 3 of n. That's the number of levels. That's the branching that we're doing at each level. Okay. But that's not what I have written here. Now, why didn't I have that?
Because your notes online are slightly wrong. Because your notes online are slightly wrong.
Because why?
Your notes online are slightly wrong.
Oh, because my notes are wrong. That's always a good possibility. Is that true?
Yeah.
Okay. Apparently my notes are wrong, and I just copied from my notes. Yeah.
I also have a quick question. The summation is to the log base 3 then? Shouldn't it go to log base 3 then minus 1?
This
Yeah.
log base 2 of n minus 1?
Log base 3 then minus 1.
Oh, okay. So that's another level of precision that I'm particularly sloppy about. Plus or minus 1. I'm usually off by those. So, yeah, log base 3 of n is how many times you divide until you get down to 1. And you're observing that you're only adding into the sum here, not all of those, you're all but the last one. Okay? And the last one is taken care of by the 450 business. Yeah. So it won't matter much, but let's do it right. Let me move this over a little bit. 3 to the I times 2. And so you're saying that's a minus 1. Okay. Now, I may choose to ignore that and then say this sum is bigger than what we're looking for. And since we're always looking for something that's bounding from above, then that would be an okay thing to do, as long as it doesn't skew the answer too much. But for the moment, let's just leave it and see what we get into. Yeah, in my notes, I have this as 450 times n. But apparently that's not right. Okay, well, we'll deal with this. Yeah, we can handle either one of them, whichever happens to be right. And that looks right. Anybody? How many people vote that this is the right? Oh, unless I'm off by 1 up there or something. Okay, so I have some people voting that this is right. How many people like 450 times n? Okay, all right. So we'll go with this one. All right, so now, how do we solve this? Actually, this 4 to the log base 3 of n, we'll see how to treat that when we look at this as well. So let's take a look at this, and that'll show us how to deal with that too. So now we just have arithmetic to do. high school level arithmetic. So we've got summation 4/3 to the I. Summation 4/3 to the I equals 0, log base 3n minus 1. All right, what does that remind you of? Definition of pi, right?
Geometric series. Geometric series.
Geometric, yeah. The definition of pi, that was a complete red herring. People were supposed to say no. Okay. Geometric sum. All right, so what's the geometric sum? Geometric sum, r to the I equals 0 through k equals, well, I'm going to cheat. Somewhere I have that written down. I thought. Oh, it's in the notes. Well, let's see. Let's see where my notes are.
Part of k plus 1 minus 1 and minus 1.
Yeah, okay. Sorry, you're all right, but I like it the form that I have it, otherwise I get confused. R to the k plus 1 minus 1 over r minus 1. And what I heard you say was 1 minus r to the k plus 1 over 1 minus r, which is, of course, the same thing. But I've got to keep my wits about me, so I want it in the form that I have here. Okay, so this is the geometric sum, and this is true for every r other than 1, because then you get a 0 here, and it doesn't mean anything. Okay, so we have that. So plugging that into here, what does that give us? That gives us 4/3 to the log base 3 of n minus 1 plus 1. So that's log base 3 of n. Okay, minus 1 divided by 4/3 minus 1, which is 1/3. So when you divide by 1/3, you're actually multiplying by 3, right? So that's 3 times that, but you were multiplying by 3 the whole thing, so that's that. Okay, so I'm going to erase this general form for the geometric sum. Okay, so now we have this thing. And what's messy about this is that you have a log base 3 of n in the exponent. We wanted a closed form formula for t of n, and it is true that this doesn't have a t in it anymore, so you could stop there, but it's not very pretty, it's not very suggestive of what it is. Ultimately, we want a big O. We want to be able to understand this thing up to a point where we can say it's big O of something. And right now, having a log in the exponent, we're not usually very familiar with the big O of how that goes. So who remembers how to deal with logs and exponents?
It's n to the power log 3 of the base.
Okay. I didn't quite hear it, but I think you must be right.
Yeah, it's basically it's n to the power log base 3 of 4 over 3 or something.
Yeah, right. Okay, good. So here's a fact that I certainly forgot from when I was in high school, but remembered relearned sometime later, that if we have x to the log base y of n, that's equal to n to the log base y of x. You can interchange what's here being exponentiated with what's here in the log. So the n replaces the x, and the x replaces the n. That's very convenient. By the way, how do you prove this is right? You just take log base y of both sides, x log base y of n equals log base y n log base y of x. Okay? Well, log base y of x to the log base y of x, what do we do here? Yeah, so this is log base y of n times log base y of x. And here it's the same thing. Log base y of x comes down. So it's log base y of x times log base y of n. And this is an equality, so that question mark gets erased. Okay, so we can do this nice transformation, which will help clean this up. What is this now? If using that cleanup, we have 3 n to the log base 3 of 4/3. And then we have the minus 3 here. So I just did this switch, but up there. And now this looks much more familiar, okay, because we have n down below, and then we have just some constant number up here. We can further clean this up because log base 3 of 4/3 is log base 3 of 4 minus log base 3 of 3. Log base 3 of 3 is 1, right? So let's do that. So this thing is equal to 3 times n log base 3 of 4 minus 1. Okay, well, we had log base 3 of 4 minus log base 3 of 3, and log base 3 of 3 is just 1. Okay? 3n minus 3. Okay, did I forget some? Oh, yeah, all right. So now that's just this sum. But looking over in T of n, we also had this n over 2 out here, which we haven't been manipulating because it was on the outside. We were just looking at the sum. And we were also forgetting this portion. So how do you clean this portion up? Just the same thing we just did. Here we have 4 to the log base 3 of n. That looks unfriendly because you have n in the exponent. But we just do the same transformation we were talking about. This makes it n log base 3 of 4. Okay? Log base 3 of 4 is some constant number. Everybody who has a calculator or has an old book of logarithms, nobody has those anymore. When I was learning this stuff, we looked these things up in books, log base e, and then you whatever. Or on your slide rule, this is just a number, log base 3 of 4. Okay? It's just some number. So this is n to some particular number. Is it bigger or smaller than 1, by the way? Log base 3 of 4. It's bigger than 1, right? Because 4 is bigger than 3. 3 to the 1 is just 3. So this is bigger than 1, so that's good. It's contributing something that's growing with n. All right, so it's 450 times some n to some particular constant. So we've got that solved. This we were working on over here, but now remember to multiply by n over 2. We can clean this up a little bit more. N over 2, 3n log base 3 of 4 minus 1. The n over 2 multiplies by the 3 also, so 3n over 2. Here we've got an n and a minus 1, so that's 3 halves n to log base 3 of 4 minus 3n over 2. Okay, again, this is just a number. Okay, log base 3 of n, whatever number it happens to be. And so finally you can just see that this thing is theta of n to the log base 3 of 4. Okay. This function is theta of n to the log base 3 of 4. Does that mean, by the way, that this recurrence, t of n, solves to theta of n log base 3 of n? 3 of 4? Where's the recurrence? It's gone. Yeah, here it is. T of n equals that. Okay. Is T of n equal to theta of n to the log base 3 of 4, or is T of n just big O of n to the log base 3 of 4? Okay, it's a tricky question, and people lack the context of why I would even ask that. And the answer is it is equal because everything we did was exact. We have an equality here, and everything we did all the way through was exact manipulation. And so ultimately, this is the right answer for T of n, and this function is theta of n log 3 of 4. So that's fine. I'm just pointing out that if in our analysis of an algorithm, you start out with a recurrence relation, and then somewhere along the line you have to make a change where it becomes like that, and then you ultimately get a function, you manipulate, you finally get a function like this. This function may be theta of n log base 3 of 4, but this function was already an approximation. So in the end, you could just say T of n was big O of n of this function here. Okay, this is a very minor point. If you're not understanding it, why I'm being so picky, don't worry. Yeah?
I mean, you could argue, since this sum doesn't really sum to an integer value at the moment necessarily, that maybe we have to go greater or less than.
Yeah, right. I mean, there's also the issue that I did all this analysis with log base 3 of n minus 1, not rounding either way, just saying, okay, we'll just assume it's a power of 3. And so if you really want to be careful, you have to see what effect that might have. And in the end, this may not end up being a theta, it might just be a big O because of that. Probably not. My intuition is that you could still conclude this was theta, but
One way with big O and one way with omega.
yeah, well, but we'll always, one way in which you would change your approximation would give you a big O, and one way would give you a theta. But we'll always want to choose it, or at least when we're trying to bound something from above, we'll want to choose our approximation so that we're on the above side, because that's the kind of result we want. We want to know that an algorithm's running time is, worst case running time is bounded by, from above by some amount. Okay, well that was kind of long and probably way more detailed than what I'll ever do in the future, but I wanted to do it once, and it introduced, anyway, this fact that people might have forgotten. It introduced the geometric sum that people may have forgotten, and just showed you how to lay out a tree again, another example of laying out a tree and seeing what's really involved in solving a recurrence relation. Now, this is the unwrapping way of solving a recurrence relation. There is another way, there are many, many ways of solving recurrence relations, but there's another very popular way to do it for the kinds of recurrence relations we're going to see in this class and the kinds of recurrence relations that often come up in computer science. And that's really by a kind of a formula. But it turns out that formula is really just a formalization of what we've been doing here. It's a way of seeing for abstract values what this kind of unwrapping and solving would give you. So this is a method called the master method. And it tells you how to solve T of n equals A, T of n over B, plus some function of n, depending on what A and B are and what the function of n is. Okay? So I'm not going to write it out. It's in the notes that's on the website. I guess I have two handouts that talk about it. The textbook doesn't call it the master method explicitly. If you look in the old textbook that was used in this class, Corman, Lysis, and Revest, the CLR, they do have it very explicitly called the master method. In our text, they sort of discuss it in passing rather than really labeling it. But anyway, it's explicitly in these notes. So I'll just show you, there are three rules. And I'll give you rule number 2. That's sort of the most familiar form. And if f of n is theta of n to the log b of a, then t of n solves to theta of n to the log b of a log n. Okay. Well, so there are 3 rules in the master method, and they all depend on what f of n is. So f of n here is just a general function of n. And a and b are constants. But if f of n is theta of n to the log base b of a, then we get this. So what recurrence relation have we seen that fits this form, that fits this rule? What about, well, I'm hoping this will work out. Tn is equal to 2 Tn over 2 plus n. Okay? This was the merge sort recurrence, right? So A is 2, B is 2. What's log base 2 of 2? It's 1. So this is n. F of n is n. Is n theta of n? Yeah, okay. Even if I had an n minus 1 here, is n minus 1 theta of n? Yeah, okay, I think it is. Well, anyway, n is certainly theta of n. Okay, so what this rule says, this part of the master method applies to this particular recurrence. And therefore, T of n solves to n log base 2 of 2, which we just said was 1. So that's n times log n. All right? So this recurrence for merge sort solves to n log n, which is what we did last time explicitly by looking at the tree. But now you have this handy-dandy cheat sheet with the 3 methods, which tells you how these things solve for most recurrences of this form. There are occasionally, you'll see recurrences of this form which don't fall into any of the 3 rules. So the 3 rules are not completely exhaustive, but they cover pretty much everything we're going to see in this class, or this kind of divide and conquer recurrence. The recurrence of this form is often called a divide and conquer recurrence. Okay. So I'll let you look at that, and I'll put something on the homework to exercise those things. All right, now I want to go on and look at another algorithm that's in some sense similar to merge sort, and will turn out to have the same running time as merge sort. The purpose is actually twofold. One is to show you that the merge sort paradigm is actually very useful. That style of algorithm actually comes up frequently. And also just to show you this particular problem where the running time is maybe a little bit surprising how fast it is. We're going to see other, at least one more, maybe 2 more algorithms of the divide and conquer merge sort paradigm. So this one, it's in section, I think, 5.3 of the book, and it's called Counting Inversions. The other reason for looking at this is actually, it turned out this particular problem has some nice applications. And yeah, maybe in this class, later on in the class, I'll show you one of the applications of this particular problem. on counting inversions. So what's an inversion? Well, first of all, we're given a permutation of n integers that is the numbers 1 through n, some permutation of that, and I'll call that permutation script A. Okay. The ith and jth entry in A where I is less than j are inverted if AI is greater than AJ. So let me give you an example of that. Example, 2, 4, here n is equal to 5. So this is a permutation of the numbers of the integers 1 through 5. Okay? And somebody tell me some of the inversions you see there. Yeah, 4 and 1. So what's in position 2? A2 is equal to 4, and A3 is equal to 1, and yet A2 is greater than A3. So that's an inversion. They're just two numbers that are out of order. They're neighboring in this example. They don't have to be in order for the definition of inversion. So these guys are inversion, but this is also an inversion. 4 is bigger than 3. That's an inversion. 2 is bigger than 1. That's an inversion. Are there any other inversions there? I don't see that there are. 4, 3. Everything else looks okay. Okay? So the general question is, given a permutation of n integers, how many inversions are there? We want to count the number of inversions. So here's our problem P. Given the permutation, how many inversions are in that permutation? Okay? And of course, we're talking about having an algorithm to answer that question, to answer that problem in general. And we want a fast algorithm. We want an algorithm whose worst case running time is small, reasonable, fast. Okay? So once we propose an algorithm, then we'll have to start thinking about what are the primitive operations in that algorithm, and then we can do the worst case running time, and the analysis of the worst case running time for that algorithm based on the primitive operations. Okay. So one question I might ask is, as a function of n, how many inversions can there be in worst case? Of n, how many inversions can there be? If you get to make up the permutation, you get to make up any permutation you like to get one with a lot of inversions, how much damage can you do? n minus 1 is the suggestion. Why?
Because you could have the first number, just have a list of numbers in the second one.
Well, let me ask this. How many pairs of numbers are there in list of n? N, what was the answer you're giving?
N
Yeah, the number of pairs, just as a preliminary question, number of pairs of n numbers, or in n numbers, is n choose 2. You're choosing 2 objects from n objects, so it's this combinatorial binomial coefficient that you all learned about in high school, and some have forgotten about, but n choose 2, and that is equal to, n choose 2 is n times n minus 1 over 2. That's the formula for n choose 2, which was mentioned here. And so that's equal to theta of n squared. Okay, so that's how many pairs there are. Now, can I get a permutation that has that many inversions? That would mean every pair would be out of order. How do I do that?
Just list the numbers in descending order.
Just, yeah, reverse the numbers, 1 through n, and write it backwards. So if we had 5 here, it would be 5, 4, 3, 2, 1. Every pair of numbers is inverted. And there are n choose 2 pairs of numbers. So 5 times 4 divided by 2. 10 pairs of numbers are out of order. Okay? So you can have every pair of numbers out of order. You can also have a list where none are out of order. Okay? Who can think of that one? Okay, 1, 2, 3, 4, 5. No pairs are out of order. And you have various possibilities in between. Okay, so given a list of numbers, a permutation of n number, oh, I'm out of time. But I want to ask my trick question first. Since you can have up to n squared inverted numbers, inverted pairs, you can have n squared pairs. If I want to count the number of inversions, do you think it's going to be possible to have an algorithm whose running time is better than n squared? Or does the fact that there could be as many as n squared inversions mean that an algorithm, to count them, has to take at least that much time?
If you're asking to enumerate them, then it takes n squared time.
Okay, I'm not going to repeat that because nobody else heard it, and I want you all to think about it before next time. So we'll pick that question up next time.